Welcome to the 7th part of the Introduction to Haskell course, and in this part we will be looking at data types in Haskell again, but this time with regards to defining our custom data types. To start off, we'll list the 3 ways of defining new types in Haskell, those being firstly type aliases, otherwise known as type synonyms as well. The second way is through use of the data keyword. So we have data declarations. And the third way is through the use of the new type keyword, in which case we have new type declarations. So let's take a closer look at each of these ways of defining new types in Haskell. We'll start off with the simplest way to define a new type in Haskell, and that is the type alias. Strictly speaking, it's not really a way to define a new type, because type aliases simply provide an alias for existing types. So we already encountered this with string being a type alias for a list of chars. Right? So we know that string and a list of chars is the exact same thing. String is just another name for it, an alias. Okay, so to define type aliases, we use the keyword type and then the name of our type alias and the underlying type that it represents. Right? So in the case of string, that underlying type is a list of chars. So in general, type aliases have only a syntactical value. They make types easier to read by using aliases, right? They don't really define a new type. So type aliases can be referenced, meaning that here, for example, we want to create another type alias for string list. We can reference the string type alias instead of having to define it as a list of chars here, for example. So we can reference type aliases in new alias definitions, and type aliases and their types are interchangeable. Generally, they're always interchangeable, and this makes sense because they are basically the same thing with just different names, right? So here I have two functions, both two of the same functions with the different type signatures, string list and the list of strings, and they also return the same, string list or list of strings. So these are completely interchangeable types as we define string list here. And so whether we define the function with this type signature of list of strings or the type signature of string list, we can use the same, we can use the function the same way. It will work with any list of strings. Now let's take a look at data declarations, which are more complex than type synonyms because they create actual new types. And this is done using the data keyword. And types defined using the data keyword are algebraic. Algebraic because they reference sum and product from algebra. And in the case of algebraic data types, sum types represent alternation, right? So they are defined in this way of a list of options such as A or B or C, and values of the sum type can take only one of the defined options. Let's take a look at an example. So here we have the definition, the data definition for the Boolean type bool. So we have the keyword data, then the name of our new type. Of course, this is a basic type in Haskell, but for this example, this is the type we are defining. And then equal sign and its list of options. In this case, this is the sum type. So we have either true or false. Okay, so any value that is of type bool can be either true or false. It cannot be both. It has to be one of the options. Okay. Another example is here. This is like a more custom type where we call it suit, representing a suit of a card. And then we have data suit is equal to either hearts or diamonds or spades or clubs. Okay, options are separated by this vertical line symbol. And right, so those are the examples for some types where values can take one of the defined options. And in general, here suit, right? So the thing on the left side of the declaration, our type name suit is called a type constructor. And on the right side of our type definition, we have hearts, diamonds, spades, clubs, and so on. And these are called data constructors. So we'll get a bit more into type and data constructors later, but for now, just remember, so type constructor is on the left side and data constructors are on the right side. On the other hand, with product types, we have combination. So instead of A or B, we have A and B and C and so on. This means that unlike some types where values can take only one of the options, with product types, values must take all of the defined options, or a valid value for a type must include all the fields of that type. And we'll see what this means with some examples. So here we have a rectangle type, and a rectangle is defined by its two sides. So we can define this data rect as rect being the data constructor as well as the type constructor. They can be the same, it's no problem. And rect, the data constructor, accepts two arguments of type double, representing the two sides of the rectangle. Okay, so this is our definition, and this is then a product type. So to create a type of rect, we need to use the data constructor, which is a function that accepts two arguments or two of the options for this type, let's say, two properties. And so data constructor rect is a function. So yes, we can actually use partial application as well, because everything in Haskell is a function. So type of rect, if we check the type of rect, we'll get accepts a double, accepts another double, and gives back a rect. Okay, so if we try to use partial application here, we say A is rect but give it only one side, then we can check the type of A and it accepts another side to give back a rect. So it's a partial application of the rect data constructor. So both the type and data constructor are actually functions that take in some arguments, or they can have zero arguments. Okay, in our case of the two previous definitions, bool and suit, they did not have, neither the type constructor nor the data constructor had any arguments, right? So they both had zero arguments, but they can have some arguments, as we'll see later. Okay. In any case, in our definition, bool is therefore a nullary type constructor, and its data constructor true or false are also nullary data constructors, right? Because bool does not accept an argument, true does not accept an argument, it's just true, false also doesn't accept an argument, it's just false, right? So both the type and data constructors are nullary in the case of the Boolean type. Now we have here an example from the Cardano node repository where we have a data definition of a type of config error, and we'll see that here it's of course a sum type because it is defined as the config error can either be config error of file not found. Okay, this is our data constructor, config error file not found, and the other option is config error no EKG, which is our other data constructor. Okay, so we see here that config error file not found takes in one argument, and that one argument is of type file path. Now here we don't know what this file path type actually is, but it's probably represents some kind of a string for the file path, but it doesn't matter. We know that this config error file not found accepts an argument. So this data constructor is so-called a unary data constructor accepting one argument. Okay, still the config error itself, the type constructor, does not accept any arguments. With data declarations, we can define functions for working specifically with our newly declared data types. So unlike type synonyms, with data declarations, they're not interchangeable with other types, right? So if we define a function that takes in a suit type for its argument, then we can only use the suit type for this function. So here we have the function suit string, which accepts a suit and gives back just a representation of a card, 3 dots here representing there is some rank of the card, and then of the suit, of hearts, of diamonds, of spades, and so on. Anyway, the way we use this function is then to give it an argument which is of type suit, right? It only works with this argument. We cannot use a string or any other type. The same goes with the product type, where we had the rectangle. So here we have a function for calculating the area of a rectangle. We say we only accept a type of rect that we defined, and we give back a double, which is a number representing the area. So we can say the area accepts an argument, and here we use the data constructor for this is pattern matching, right? So the brackets simply represent this is a one argument, right, all together in brackets, and it's composed of the data constructor and its two arguments. So rect accepts A and B, and what we want to give back is A times B, as that represents the area, right? So we can use this function specifically for our rect type, and if we say a rectangle with sides 2 and 3, then the area will be 6. Product types can also get more complex as they start to have more fields, and just writing the fields out in their respective types does not give enough information to be understandable to someone reading the code, right? So for example, here we have a declaration of a type for a company, right? So this type is supposed to represent a company. We have a data constructor that accepts 4 arguments, 2 of type string and 2 of type integer, right? So just from reading this line, I can understand that the type is supposed to represent a company, but what these properties mean, these fields of string and integer, I can kind of only guess. I don't have an intuitive way of understanding what they're supposed to represent. Okay, so this is where field labels or records come in, and they provide us with a nicer way to write our code, keep it readable and intuitive. So it is more user-friendly to use field labels here, and they also automatically provide getter functions for each of the fields defined. So let's define this data type company by using field labels here. So the syntax is a bit different, and we still say we use the keyword data. We say our type constructor is company, and on the right side of the equation we have company, the data constructor, and then here we open the curly braces, and inside the curly braces we put our fields with their respective types, but we give the fields names. Okay, so here I have C name, C address, C year, and C NRE. Now, okay, NRE maybe it's a bit cryptic, but anyway, C name stands for company name, and this is pretty intuitive what it means, right? So it's a string for the company name. Same goes for address. Company address is a string that represents its address. C year, it could be a year of founding, a year of foundation of the company, an integer, and C NRE, I meant to say it's the company number of employees, also as integer, right? So here it's much more easier to understand what each of the fields of this type actually represents, just by reading the type definition, right? Unlike the one here above. Now, what I meant with providing getter functions, here we have an example of C being the company, so using the company data constructor and giving it its arguments, the name, the address, year of foundation, and number of employees. And then if we want to get a certain field from this company type, we can just call the name of the field, and this represents the getter function. So here we call C address, which represents our field C address, and we call it on C, which is a type of company. So C address of C gives us back the address, C year of C gives us back the year of foundation, and so on. So this is another extra bonus that we get when we define data types with field records. Lastly, we'll look at new type declarations, which are something in between of type synonyms and data declarations. So new type declarations can be only used for defining types that have a single data constructor that accepts a single argument. So let's take a look at an example here. We use the keyword new type, then our type constructor, or basically type name, IP address. And then this type, like we said, has to have only a single data constructor, in our case here IP, and a single argument it accepts, in our case here string, okay? So unlike a type synonym, this is not simply a synonym for the type string. It is a new type, which is sort of like a wrapper for string. So this means that it's not interchangeable with string. Any function that we define as using IP address type, we have to give it a real IP address type for it to work. We cannot give it just a regular string. It has to be wrapped in this new type. So there are some performance benefits to using new type instead of data when possible, because as we know, new type can only be used with a single constructor with a single argument, so it's quite limited in that regard, where data is not. But if we can use new type because it has some performance benefits, because basically new type doesn't create any runtime overhead, whereas data does, because data really defines real new types in Haskell, where new type is sort of just a wrapper for existing types, and on runtime it can simply be removed, and basically performance is better if we can use new type instead of data. That's the end of this presentational part. We looked at the 3 ways of defining custom types in Haskell, and now let's get into the practical session to see this in code. So let's check out these ways of defining new types in Haskell. We first talked about the type keyword, which is used to define type synonyms, and the example we had was a string list. We create a synonym string list, which stands for a list of strings. Okay, so this is our first and simplest way of defining new types in Haskell. Now the thing is, it's not really a new type, right? It's just an alias, and these 2 types are now completely interchangeable. Okay, so let's say I set A to be equal to some list of strings, Okay, and I can say it's a list of strings, or I can say it's a string list. Either way. And now imagine that we have some function that takes in, let's say it takes in a list of strings specifically, and gives back a boolean. It's just some silly function. Let's say if the list is empty, it's false, and if anything else, then it will give back true. Okay, so now this function works with a list of strings, and A is a string list. So can we actually use A to feed this function? Well, let's see. So let's set B to be the application of F1 to A, right? And the compiler is not, the IDE is not complaining about anything, right? Not complaining about types. So this seems fine. And indeed it is, since they are just synonyms. If we load this up, everything works fine. If we check A, it's our list of strings, and B evaluates to true, since it's not empty. Next, we saw data declarations, which do actually define new types that are not interchangeable with anything, but are actually their own types. So we learned about sum types and product types. Okay, so the example we had for sum type was, for example, a boolean, but which is like either true or false, right? But we'll use the suit type we had to define hearts or diamonds or spades or clubs. Right, those are the four suits of playing cards. And now these could read something like strings, right? They just, they're simply values. But if we want to make a function that takes in a suit and gives back, I don't know, again, let's say it's a silly function. And we just return, not true, sorry, but boolean. Then F2, for example, if we match with hearts, we return true. And if we match with anything else, we return false. Okay, now let's reload this and just do it in GHCI. So F2 applied to hearts as a string cannot work, right? Because the type is different. A list of chars, a string, is not the same as a suit. But if we remove the quotes and just give it hearts as the data constructor for this type, then everything works fine. Okay, so that's an example of a sum type where the value of the type can have one of these options. So it can have one of these data constructors. Now let's take a look at the product type, where we saw data constructors with multiple arguments, right? So not nullary data constructors, but in this case, the example we saw with the rectangle is a binary data constructor. So we create our new type with data rect. We set the data constructor to be the same as the type constructor rect. And now we list its two arguments, right? We list their types. In this case, we represent the two sides of the rectangle with two double types. And now this rect is a data constructor that accepts two arguments, so it's a binary data constructor. Okay, so we can create a rect type if we say here C or maybe R. And we call the data constructor, which we know is a function. And we already see here that this accepts two doubles to give back a rect, but we can just apply the arguments here right away. And now we see that what we get is a full rectangle, since both of the arguments are supplied right here. We can also create functions specifically for our defined types. So we had in the presentation an area function that takes in a rectangle and gives back a double that represents its area. And so we pattern match. So we know that we accept a rect, but what is a rect? In this case here in the type signature, rect is the type constructor, right? Not the data constructor. So rect as a type constructor is equal to all of this. Okay, so in our pattern matching, that's exactly how we match, right? We say the data constructor that we want to pattern match against, which is rect for the type of rect. It might be a bit confusing, but I think you understand. So we match exactly on this data constructor. And we name the sides A and B, and to give back the area, we just multiply A and B. Right, so this now works fine. We can say what's the area of R, and it's 6. Okay. So that's an example of a product type. And then now let's look at a more complex product type that we saw also, the company example, which has more fields that it's not so clear what each field represents. So we can use field records to make the code more readable and automatically provide getter functions. The definition that we had, I'll put here field records. The definition that we had of a company was data company is equal to the company. So company, the data constructor, here company, the type constructor, and company data constructor accepts 4 arguments, string, int. Okay, so from this, what do we know about this type? Okay, it's supposed to represent a company, but what are its arguments for the data constructor? Not really clear, right? So we can make this much more intuitive and better to read if we define data company with field records. So then again, we say data company, it lists the data constructor company, but in this case we open the curly braces and we name each of the fields to give it an intuitive name. So in the presentation it was C name, which is a type of string. Then the company data constructor also needs a C address, the company address, also in the format of string. And then the integer is a company year of foundation, and it was CNRE as number of employees. Okay, now again, our company data constructor accepts 4 arguments, same types as here, but it's much more clear what these arguments represent in the actual type. So let me reload this and see the, or better yet, I'll code it here. Let's say we have a company. We create a company, and so in this case we are using the curly braces and the field records with the double colons to signify the types. But if we want to then create a type, we can still use the record labels, and we set the equal sign to assign a value to each of the labels actually. So my company, C address, some address, we have C year and C NRE. Okay, so we can actually create an instance of this type using field records as well, assigning the values like this. Okay, and then we can write functions for our new type. Let's check here. So F3 can be a function that accepts company, and let's say it gives back a string. And, since we have the getter functions available, we can just call the company argument a name, let's say X or C. And if we want to get a field, or for example, we want this function to print some message about the company name, like this company is called, and then we want to print its name, right? So we can just say CNAME of the company, right? And then we can add dot at the end. So if we reload this and we say F3 of our company that we defined, then we get back the CNAME, right, with the getter function. A very simple but very useful. Lastly, we explore the new type keyword, which we said is something in between type aliases and data declarations. The example we had was an IP address type that we defined with the data constructor IP and then the string. So we know that new type can have only one data constructor with exactly one argument. Okay, so you can think of new type as basically a wrapper around an existing type, in this case string, right? And IP is our data constructor, the wrapper. Now, why is it different from type alias, right? Type alias would be something like IP address is equal to string, right? So IP address is just another name for string, but actually for the example of IP address, it's not really what we want, right? Because string and IP address are not actually synonyms, right? So when we define our new type as IP address, then we cannot interchange it simply with string. We have to use the data constructor IP. Say if we have a function that we want to work with the IP address, and in this case, let's just make a silly function. So F4, and then we can pattern match. We know we will get IP and then some string XS. And for example, if we get an empty string, we can say false, and F4 matched on some string XS will be true. Okay, so if we load this in GHCI and we say F4 applied to some IP. Okay, this doesn't work because I tried to apply it with simply a string, so a list of chars is not the same as IP address, right? So, but if we wrap this, we probably need to scope it, right? So if we wrap the string into our with our data constructor IP, then everything is fine, right? And same for if we give it an empty string. If we give it an empty string, then we get back false, right? Still, it works because it's wrapped in the constructor. So it's not really a synonym. It's a new type, but it's sort of a very... it's limited in what we can do with this new type. However, it is useful to use new type instead of data if the type is really going to be this simple because of some performance reasons. So now let's do the katas for this session. Now, katas on this sort of type declarations are a bit scarce. So I did find 3 that we can use. We'll start with this one, say hi. They're all pretty simple. This one is says to write a function, say hi, which will take a person record, right? And our person type is already defined here as an input, and return a string. Okay, hi, I am first name, last name, and it's nice to meet you. We see some I is here lowercase, U is uppercase. We need to make it exactly like this, even though it's not really grammatically correct. You will need to define the record type person with fields first name and last name. Well, okay, it says here we will need to define it, but it's already defined for us if we try to solve it in Haskell. So it's defined here as data person, and then using field records says first name, last name, 2 strings. Okay, so we don't need to write this ourselves, but it's pretty simple anyway. Okay, then we have say hi, accepts a person, gives back a string. Okay, and person here is p as the argument to the function, and so we can just fill in this string, so I am, and then we want to add the first name. So since this definition of data person is using field records, we can simply say first name of p, and this getter function will get the first name. Then we need a space between this and the last name, which we can get the same way, and then we need the end of the string, and it is nice to meet you. Okay, so that's it. We can load Katas say hi. One module loaded. Now we need to create a person to test this. So we'll say P is a person of John Doe as first name and last name. Okay, so we can create an instance of the person type without using field records if we don't want to. If it's defined this way, we can still use first name and last name here. Right, so the instance of a person declaration can be whatever we like. But if we don't define the type using string records, then we don't get the getter functions. Okay, anyway, we have our person P here. Okay, show person doesn't exist. We'll get into that in the next one of these katas actually, and next session as well, next video. But for now, we just want to call say hi on person P, and it will say hi, I'm John Doe, and it's nice to meet you. Okay, so that's the first kata done. Now let's go into this person type string representation kata. And it says write a new type person with properties first name and last name, implement it in a way that it will have a nice string representation. For example, John Smith. So it should print the first name space last name when we try to show it. Okay, this is what I was just trying to say, because our instance of person from say hi does not have an instance for show. Okay, so basically when we try to print P, when I try to do it here, Haskell is telling us, or GHCI is telling us, I don't know how to print it because you didn't tell me how to. Okay, so now it's our job, and it's really a sneak peek for the next video, because then we'll get into type classes, and show is a class. But for now, let's do it here, as it is pretty simple. And in general, when you define types, when you define new types, you usually want them to have some kind of string representation, and that may be a custom one. So data person, we have to define it in this case, and we can define it as it was defined in the previous one, right? So it has first name, which is a string, and it has a last name, which is also a string. Okay, that's our data person declaration. And now we want to, so we know that no instance for show person. So we need to create, we need to make person, the type, an instance of the show class. So we do this by saying instance as the keyword instance, show person, where and then the method show, and now we just define the method as a function. So show is a function. We match on the person first name, last name, and we say what this function should return, and we know that it returns a string. Okay, so we will just return the first name plus plus a space and the last name. Okay, so the syntax is instance, the keyword, then what class we want to make an instance of, in this case show, and then what type we are working on to make an instance. So in this case instance show person, where show, we can also add the type signature, show takes in our type of person and returns a string representation of that type. And for us, this is our show function. When we give it a person with a first name and the last name, we'll return a first name joined by a space and the last name. Okay, so if we load this person type kata, and if we define a person again as John Doe, I'm not sure if anything's gonna get overwritten because I already loaded the previous kata, but let's see. So now if I, okay, it's loading person from this definition, or since they're the same, okay, doesn't matter. Anyway, this worked, right? So now we have an instance of the show class for our type person, and if we try to print it, we directly get the string representation that we like. So in the previous kata, if we actually did that here as well, instead of writing first name P and last name P, we could say, I'll copy this over, we could say it like, hi, I am, and then simply show P, right? Now here it's it says no instance for show, because in this module there is no instance for show, but this is what we could do, right? If we, with what we did here. Okay, so that's the string representation for the person type. And now let's get into the last kata for this session, called Unix. This is another simple kata regarding some custom types. So on Unix system type files, they can be identified with ls-l command, which displays the type of the file in the first alphabetic letter of the file system permissions field. Okay, so if the first character matches dash, then we have a file. If it's a D, then it's a directory, L for symlink, and so on. We have a list of things here. And in this kata, we should complete a function that returns the file type as a string regarding the file attribute given by the ls-l command. Okay, for example, if the function receives dash at the first character, right, it should return file. Okay, so in this case we have some, and in my IDE this is not gonna work, right, but in the Code Wars web app we have this some preload, which is probably where this data file type is defined, and that's why it starts commented out. But since locally I don't have this module, I cannot load it, I will comment this out and I will define file type here directly, right? So file type is a list of these things. It can be file, directory, symlink, character block, door, socket, or pipe. And now we simply have to check if we get a string, which file type do we return. Okay, so we can do this with pattern matching, because we know we are only looking at the first character of this of this string that we will receive. So we can just look at the head, and the rest we can ignore, use a wildcard. We don't need it, right? So then we can do even one better. Instead of looking at x and then comparing like x is equal to dash whatever, we know that with pattern matching we can match on direct values. So we can say here, if the head of the list is a dash, then we will return file, right? And so we can do this for all the cases. So if it's D, then we return directory. I think if it's a capital D, yeah, capital D is a door. Then we have L for symlink. We have what is this character? C. Character, we have a socket, S for socket. We have P for the pipe. I think that's everything. Door, socket, pipe, block, character. Yeah, we are just missing the block. Okay, so B for block, and that's it. And this is enough. Of course, this is not exhaustive because the string could start with any other character as well. So we could say like, okay, if we match anything else, we return by default file, for example. But in general, with this function, we know that these are the only options that we can get as at least as valid strings for this sort of function, right? Because the ls-l command can only return a list that is contained here. So we pretty much know we're not going to get anything else, but still, if we wanted a default option, we can do it this way. And okay, that's it. It's another simple kata, just pattern matching on the first character to return the correct type. And that's it. That's the end of this session. It was a bit of a shorter one and a simpler one. We explored the three ways of defining new types in Haskell, or one of them is just defining type aliases. And that's it for now. So thank you for watching, and see you in the next video.